All right, so percent yield seems easy, right? It's just a plug and chug sort of formula. But students lose points all the time because they either use the wrong numbers, they skip the limiting reactant step, or they even just mislabel actual versus theoretical yield. So let me show you the clean way to get the answer right every time, and I'll walk it through with a full example. But before we actually get there, before we actually, walk through the problem, let's quickly break down what percent yield actually means, because this is where a lot of people might mess up. So, percent yield is simply a way of measuring how efficient your chemical reaction was. Like, let's say you were supposed to get 100 grams of a product, but you actually got only 80 grams. Well, this means you didn't fail, but you had an 80% yield. So, the theoretical yield, what does that mean? Theoretical yield is really what the math says that you should get. The theoretical yield is the number you get from stoichiometry, right? It's the maximum amount of product that you'd get if everything reacted perfectly with no loss. That is what your theoretical yield is, and that's what it is. It is theoretical, right? It is ideal. It's the ideal value that you calculate using your balanced equations and mole ratios. It's kind of like saying, let's say I had 5 pizzas and 5 friends, and each person eats 1 pizza, then all 5 pizzas should be gone, right? That would be ideal. But that is a theoretical scenario. Let's say one of your friends wasn't as hungry, so now you have some leftovers, right? That's life. That's real life, right? Things aren't exactly as you plan. Things go wrong. Nothing is perfect. I don't see why chemistry should be any different, right? So then what is our actual yield? The actual yield, again, is also like what the name suggests. It is what you actually get from an experiment. The actual yield is what you got in the experiment, what you physically measured on the balance at the end. It's the real data. It's almost always less than what the theoretical yield is. But why? Well, because reactions aren't perfect, right? Maybe there was some spillage, there were some impurities in your sample, you had an incomplete reaction, or maybe even some leftover product was stuck to your container as you were pouring it onto the balance to measure it. All of these could give you an actual yield of less than what your theoretical yield would be. So then what is this formula, this plug and chug formula that we were talking about? Well, our percent yield can be found simply by taking our actual yield and dividing by our theoretical yield. Theoretical yield. This number would give us some decimal value, and so if we want our answer as a percentage, as percent yield would suggest, we just have to multiply this by 100% to get our answer as a percentage. So you take what you actually got and divide by what the math says that you should have gotten, multiply by 100 to get a percentage. So just as one kind of final clarifying analogy, if your theoretical yield is like what the recipe says the cake will weigh, then your actual yield is what your cake actually weighs after you bake it. And the percent yield will tell you, or just tells you, how close you got to the recipe. So I hope that makes sense. It kind of clears any doubts you may have had. And so we can go directly into the problem at hand now. So the problem says that we have a 25-gram sample of aluminum which reacts with 60 grams of chlorine gas, yielding 90 grams of aluminum chloride, which we collect. So what is the percent yield? Well, we're also given, this balanced chemical equation right here. Well, how do we do this? We say, first, number one, that we have to convert our grams to moles. We are reacting 25 grams of aluminum and 60 grams of chlorine gas. So first we convert both of these to moles. How do we do this? Well, simple enough. We just take our molar mass, right? Let's say we have our 25 grams of aluminum. Looking at our periodic table, we find that the molar mass of aluminum is 26.98. So 26.98 grams of aluminum per 1 mole of aluminum. Canceling out our units of grams per aluminum gives us an answer of approximately 0.927 moles of aluminum. Now we do the same deal for our chlorine gas. So we have 60 grams of chlorine. Remember, that is Cl2, not Cl, because chlorine is a diatomic. I'll explain what that means actually in just a minute, but basically in context that means our periodic table actually tells us that chlorine has a molar mass of 35.45 grams per mole. But this is for chlorine, the monoatomic. But in practice, chlorine is going to be a diatomic, meaning that this is not what we're going to be using for the molar mass. Really, what we have to do is multiply this by 2 because this is Cl2, giving us our molar mass of 70.90 grams per mole. 70.90 grams per mole. Canceling out grams of chlorine, moles of chlorine, gives us an answer of approximately 0.846. 846 moles of chlorine. Okay, and again, just a side note, in case you guys are ever struggling to remember what your diatomics are, there's a simple mnemonic device that I like to use, Hunkel-Brief. Hunkel-Brief. That's hydrogen, oxygen, nitrogen, chlorine, bromine, and fluorine. All of these are going to be diatomics. So whenever we're doing a problem like this, it's important to remember that it is going to be H2, O2, N2, Cl2, Br2, and F2. So important to keep that in mind when you are going to do some sort of grams to moles or moles to grams conversion. So yeah, that is Hunkel-Brief. But anyway, now that we have converted our grams to moles, we can move on to the next step, and that would be finding the limiting reactant, right? We have to always determine the limiting reactant unless it is stated in the problem already. In this case, it isn't, so we have to determine what is our limiting reactant in this case. So let's just take note of these numbers very quickly. We can write them on top here so we don't forget. We got our aluminum was 0.927 moles, and our chlorine was 0.846 moles. So just keep those numbers in mind. And now determine the limiting reactant. Again, looking at our balanced chemical equation, we can see that we have 2 moles of aluminum reacting with 3 moles of chlorine to give us 2 moles of aluminum chloride. So let's just say chlorine, we can use chlorine and see how much aluminum is needed for our 0.846 moles of chlorine to react. Well, 0.846 moles of chlorine. Let's just set this up stoichiometrically. That should be the easiest way, right? Well, our balanced chemical equation tells us that for every 3 moles of Cl2 we need 2 moles of Al. Well, this tells us that we need 0.564 moles of aluminum is needed. And, well, we see that we have 0.927 moles of aluminum. So we have enough. Well, actually more than enough. So we have an excess of aluminum, and that means that our chlorine is the limiting reactant. Chlorine is the limiting reactant. Let's remember that and get this out of the way. Well, chlorine is limiting, so we have to use that limiting reactant to calculate our theoretical yield, right? We'll use the limiting reactant of chlorine to find out how much AlCl3 should form. And we use our mole ratios from our handy balanced chemical equation, again, to do that. So we take our 0.846 moles of chlorine, that limiting reactant. According to our equation, every 3 moles of chlorine that reacts, we should be getting 2 moles of aluminum chloride, AlCl3. Canceling out our moles gives us an answer of 0.564 moles of AlCl3. Well, now we need our answer to be in grams, right? We're dealing with grams in the problem statement, so let's convert this. How do we do so? Well, again, we just need our molar mass of aluminum chloride. I actually did this calculation off screen, And so I will not show the work here, though again, if you wanted to do it yourself, it would be pretty straightforward. Remember, you're just taking the molar masses of the individual elements that make up the compound and adding it up together. So, well, if we do that, we see that for every 1 mole of aluminum chloride, we actually have 133.33 grams of AlCl3. Canceling out our units of moles gives us an answer of 75.2 grams of AlCl3. This here is not our final answer, but it is our theoretical yield. That is how much we should be getting according to all this fancy stoichiometry math that we just did. Okay, well, that should be straightforward enough, right? What we do next? Well, we know our percent yield formula, right? Let me just write it out again. Percent yield. That is just our actual yield divided by our theoretical yield. Well, we have our actual yield in the problem. That is 90 grams of AlCl3. Remember, actual yield, the one that you actually got it, we actually got when we collected it from the experiment. And theoretically, what we should be getting is 75.2 grams of AlCl3. And don't forget to multiply by 100% to get your answer as a percentage. This gives us an answer of 119.7%. Is that right? I mean, it's over 100. How is that even possible? Well, that is actually the correct answer. This is 119.7%. That is our percent yield. How does that work? Well, suppose your sample was impure, right? Again, like we said, our actual calculations or our actual results of an experiment are often not exactly what we would expect to get from calculations. Let's say, as an example, right, in your experiment, you need to weigh your sample totally dry. That product needs to be a dried product that we weigh on the balance. But let's say it hasn't completely dried when you're weighing it. That means what you're weighing is going to be your sample plus some amount of water, which means that that mass that you weigh on the scale is actually going to be higher than the mass of just your sample, because we're going to be having the mass of water in there as well, which means that this actual yield that you supposedly measured is going to be higher than what you theoretically should have gotten, because in your theoretical calculation, you're talking about a perfectly 100% dry sample. Well, that realistically is not going to happen in an actual experiment. So in your actual experiment, you may have some water or some other impurities that will be contaminating that sample, leading to a value that is actually higher than what you should have gotten theoretically, per se, according to calculations. So that is exactly how we do this type of problem. And that is often a mistake, well, not a mistake, that's something that teachers may put on your exam or your professor may put on your exam to make you think that you might have messed up. You get a percent yield of over 100, that is totally fine. I would always suggest checking your work at the end of every problem, but do not be startled if you see that you get a percent yield of over 100% like we did today. All right, so the steps to convert or steps to go about any percent yield problem and make sure you get it right every time is first, obviously, we go converting to moles. Number 2, identify that limiting reactant. This is what people often forget. Identify that limiting reactant. Don't be the person who forgets to do that. And 3, use that limiting reactant to find your theoretical yield. Calculate that theoretical yield. How much product should you be getting in theory? And finally, it's just plug and chug. Plug that theoretical yield or plug your actual yield over theoretical yield and calculate that percent yield. And this should just lead you to the correct answer every time if you just follow these steps. So again, don't forget to always check for the limiting reactant, even in percent yield questions. That's the step that most people forget. Anyway, if this helped, please check out my other videos on limiting reactants, empirical formulas. Both are very tightly connected to this type of question. And again, like and subscribe if you want clear chemistry breakdowns like this in the future, and please leave a comment for any future suggestions of other topics that you guys struggle with and would like me to make a video for. Thank you again, and I'll see you in the next one.